Hi everyone, welcome to the Earth Science Region to View podcast series created by Hammock's Middle School Earth Science Department. Today we're going to focus our attention on the sequence of events. So really what we're going to do today, we're going to talk about something called relative age. So geologic history is a very, very important concept here because you're dealing with a huge amount of time. You're dealing with about 4.5 billion years worth of our Earth's history. And the thing that geologists have to do is they need to be able to read the clues in the rock, whether it's the animals, whether it's the plants. There's a lot of different clues within the rock in terms of fossils. And talk to us about the environment, the atmospheric condition, whatever it may be. The geologic history is really going to be locked up in the rock itself. So what we look for here is we look for what's called a sequence of events. What happens first, what happens second, what happens third, what happens fourth, and so on. Okay, with your geologic dating here, okay, what you want to do is you want to compare the age of a rock to another. It's what we call relative dating or relative age. That's very different from actually putting an actual numerical value on a rock itself, in which we would call absolute age. So there are a couple key concepts here in terms of trying to understand the sequence of events. When you talk about being something that's being older, that's going to be something that happened first. Something that's younger is going to be something that happened more recently or something that happened last. Okay, and what we do is we're going to look at examples of outcrops of bedrock. Bedrock is just the rock underneath the surface. If it's exposed at the surface, it's what we'll call an outcrop. So here's a picture of an outcrop right there. Now, there are a number of principles that help us understand the sequence of events. And the first one's the principle of uniformitarianism. It basically states that the present is the key to the past, and basically the processes that are going on today, like volcanic eruptions, weathering and erosion, plate tectonics, also happened in the past. So it kind of gives us a little bit of a window to the past in terms of how the Earth was shaped millions and millions and millions of years ago. Principle of original horizontality just basically states that rocks are laid down in layers that are horizontal. That's just not familiar because that's how sedimentary rocks are laid down. Any kind of faulting, folding, tilting are always going to be younger than the rock itself. Rock has to be laid down first before it gets altered. So you can see the horizontal rock in this picture. No deformation to it. Oldest on the bottom, youngest on top. And that leads us to the principle of superposition, which basically states that the rock layer on the bottom is going to be the oldest, and the rock layer on the top is going to be the youngest, just like I recently stated. Okay, sometimes you get layers that are overturned, which means that the layers get turned upside down. In that case, the youngest would be on the bottom, and the oldest would be on top. But the Regents has to let you know if that actually happens. So you can see here, in terms of your rock layers, the youngest on top, the oldest on the bottom. Okay, so very, very important to understand your sequences with those rocks. Now, you also have the principle of cross-cutting relationships, and that deals with intrusions, which is magma, which is igneous material, magma that's deep inside the Earth, that's always going to be younger than the rock around it. And you also have extrusions, which are lava flows. They're also going to be younger than the rock around it. Any type of deformation or any kind of alteration to the rock is always older than the processes that touch it, whether it's intrusions, extrusions, folding, faulting, or tilting. Now, intrusions and extrusions, because you're dealing with igneous or any kind of magma or lava, you have to deal with contact metamorphism because you're dealing with such intense heat here that magma or lava is going to touch the rock, it's going to bake it in the process of contact metamorphism. So you'll see that this is an intrusion because you have contact metamorphism on both sides. If you have contact metamorphism only underneath, only on one side, it's an extrusion. In this case, it's a buried lava flow because you have the shale on top of it. There's an actual example of what an intrusion might look like. That white line going vertically through the picture, that's an intrusion. Now, contact metamorphism is important because certain rock is going to turn into something new. So, for instance, limestone metamorphoses into marble, sandstone metamorphoses into quartzite, and shale metamorphoses into slate. That's all in your metamorphic rock chart, okay, on page 7 in your reference table. Now, you also have what are called principle of inclusions. Sometimes the bedrock is going to break off and fall into the magma or lava. Okay, sometimes that magma or lava is not hot enough to melt it. So what's going to happen is that little wedge is going to work its way into the magma or lava, and the inclusion is always older than the magma or lava. That rock had to have been there first before the magma or lava actually touched it. So there's a nice inclusion within some old lava. Now, folds, faults, tilting, any kind of deformation, they're always younger than the pre-existing rock. Rock had to have been there first before the alteration actually occurred. So when you talk about folding, faulting and tilting, there's a picture of a fault. There's a fold. There's some tilted rock that's also faulted as well. So here's a regions diagram that shows an intrusion. You notice that because you have contact metamorphosis around the whole thing, and a fault. You know the intrusion is older than the fault because the intrusion is broken like the other rock layers. If this question actually pertained to what rock formed at point A, which is contact metamorphism of sandstone, that would have been quartzite. And again, you see the folding underneath the horizontal, the folding of the rock layers. Very important to include that sequence in because that's going to be deformation of the rock. Folding is always younger than the rock around it. Now, you can get really picky here and really technical in terms of the sequence of events, in terms of internal characteristics of rock. So the sediments and crystals within a rock are always older than the rock itself. So we take a look at conglomerate. Those rock pebbles that make up the conglomerate rock are older. They had to have been there first. Same thing with the crystals in the granite there on the right. Those crystals had to have been there first before the rock actually cooled and solidified into that big chunk. Now you can also get unconformities, which are buried erosional surfaces. And what's important here is that they show a gap in the geologic rock record. Rock is actually missing in this case. It's really a three-step process. It's uplift, it's weathering and erosion, and subsidence. Uplift means rock is forced out of the water. Subsidence means that rock falls below water level in order for deposition to occur back. So here's an unconformity right there between the horizontal rock on top and the folded rock down below. And some regions diagrams as well. Here's a nonconformity, disconformity, and angular unconformity. So not a big deal that you know the different names, but it's important that you understand where the unconformities are. So there's one unconformity there. The second unconformity right there. You see the boundary between the rock layers. It's very stark. And then the third unconformity is right there. So make sure you understand where that's going to lie within your sequences. So let's put this into order, starting with the oldest layer on the bottom. So it's going to be G, which is your limestone. Then you're going to have F, which is your shale. Then those rock layers are going to be tilted and faulted. Then you're going to come in with intrusion A, then intrusion B. Then comes our unconformity. Then you're going to get uplift, weathering and erosion, then subsidence. Then D is going to be your sandstone. E is going to be your shale. H is going to be your limestone. Then you're going to have intrusion C because it's touching every single one of your rock layers. If you really want to get technical, you can have uplift, weathering, and erosion at the surface as well. So with that being said, hopefully this gives you a little insight about your sequence of events, and we'll talk to you soon.